So we're going to start with atomic structure and periodic trends. This is Unit 1, electron configurations, orbitals, and quantum numbers. Full and condensed configurations. Follow the Aufbau principle, filling lowest energy shells first. Pauli exclusion principle, max 2 electrons per orbital with opposite spins. And Hund's rule, parallel spins before pairing within a subshell. Example, iron Fe, Z equals 26, full, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Condensed AR, 4s2, 3d6. Remember, condensed is just like the gases, you know them, the gases on the far side. Quantum mechanics framework and principle, shell level 1, 2, 3. L, angular momentum / subcell shape. So 0 equals S, 1 equals P, 2 equals D, 3 equals F. Valid ranges, 0 is less than or greater or equal to L, and then L is less than or equal to N minus 1. ML is magnetic orbital orientation. Range, negative L is less than or equal to ML, which is less than or equal to plus L. MS, electron spin orientation, value must be either positive 1/2 or negative 1/2. Periodic trends breakdown, trend metric, effective nuclear charge, left to right across a period increases predictability. Top to bottom down a group decreases slightly / remains steady. Core electrostatic driving force, more protons added to the same primary shell, minimal shielding change. Trend metric atomic radius, left to right across a period decreases, top to bottom down a group increases. Core electrostatic driving force, higher ZeFF pools, valence shells tighter. Additional principal energy shells expand radius. Trend metric first ionization energy, left to right across a period increases, top to bottom down a group decreases. Core electrostatic driving force, tighter pull requires significantly more energy to attract outer valence electrons. Trend metric electronegativity, left to right across a period increases, top to bottom down a group decreases. Core electrostatic driving force, stronger nuclear force easily attracts shared bonding pairs close to the core. Accurate Lewis structure and Vesper geometry flow. So sum valence electrons, total all valence electrons, add / subtract electrons matching the polyatomic net charge. Form backbone, place the least electronegative element, never hydrogen, as the central atom, connect with single bonds. Satisfy octets, distribute lone pairs to terminal atoms until octets are full, then dump any leftover electrons onto the central atom. Form double / triple bonds if the central atom lacks an octet. Pull lone pairs from terminal atoms into multiple bonds. Note, group 3 elements B, aluminum, can be electron deficient. Period 3 and below can expand their octet up to 10 or 12 electrons due to vacant d orbitals. Vesper geometry and bond angle adjustments. So steric number 4, bonding pairs 4, lone pair 0, electric domain geometry, tetrahedral, molecular shape tetrahedral, ideal angles 109.5 degrees, real adjustments and rationales, perfect symmetry, example CH4, steric number 4, bonding pair 3, lone pairs 1, electron domain geometry, tetrahedral, molecular shape trigonal pyramidal, ideal angles 109.5 degrees, real adjustments and rationale, less than 107.3 degrees due to lone pair / bonding pair repulsion. Steric number 4, bonding pairs 2, lone pairs 2, electron domain geometry tetrahedral, molecular shape bent, ideal angles 109.5 degrees, real adjustments and rationale, less than 104.5 degrees, two intense lone pairs squeeze bonds together, example H2O. Steric number 5, bonding pairs 5, lone pairs 0, electron domain geometry, trigonal bipyramidal, molecular shape, trigonal bipyramidal, ideal angles 90 degrees / 120 degrees, real adjustments and rationale, equatorial versus axial axis, example PCl5. Steric number 6, bonding pair 6, lone pair 0, electron domain geometry octahedral, molecular shape octahedral, ideal angles 90 degrees, real adjustments and rationale, highly symmetrical, SF6. Molecular polarity versus intermolecular forces, IMFs. A molecule is only polar if it contains polar covalent bonds 0.4 less than or equal to the electronegativity, but is great. But the electronegativity is greater than that, but less than or equal to 1.7, and is structurally asymmetrical, preventing bond dipole vectors from canceling out. London dispersion forces, LDF, universal to all matter, scale with total electron count and surface area, greater polarizability. Dipole-dipole interaction, present in net asymmetrical permanently polar molecules. Hydrogen bonding superstrength dipole interaction occurs exclusively when H is directly bound to NO or F. Problem, rank the following compounds from lowest to highest boiling point. CH4, CH3, Cl, CH3, OH. Justify your answer. So step-by-step rationale. CH4 is a symmetrical tetrahedral molecule. Its bonds are nonpolar, making the molecule completely nonpolar. It relies solely on weak LDFs, lowest boiling point. CH3Cl has an asymmetrical tetrahedral geometry with a higher polar CCl bond. This yields a strong molecular net dipole, adding dipole-dipole interactions on top of LDF's intermediate boiling point. CH3OH features a high polar OH bond. This triggers extensive intermolecular hydrogen bonding, requiring the highest thermal energy input to break highest boiling point. Hybridization theory. Determine hybridization directly by evaluating the total number of electron domains, bonding set plus lone pairs surrounding the central atom. 2 domains, sp hybridization, linear layout, example ethine. 3 domains, sp2 hybridization, trigonal planar layout, example ethene. 4 domains, sp3 hybridization, tetrahedral layout, example methane. Unit 3, Organic Chemistry, Naming Functional Groups and Reactions. IUPAC Systematic Nomenclature Core Rules. Find the continuous carbon backbone that contains the principal functional group to establish the root name. Number the root chain starting from the edge closest to the principal functional group to give its suffix carbon the lowest possible locator number. Identify secondary branches, alkyl groups, halogens, and order them alphabetically. Example, ethyl before methyl, ignoring multipliers like di, tri, or tetra. Reaction predictor protocols, the 5 major vectors. So addition reactions, breaking a pi bond to add 2 new atoms across an alkene/alkyne. Markov-Nikov's rule, when adding an asymmetric reagent, HX or HOH, the hydrogen atom selectively binds to the alkene carbon that already holds the higher count of hydrogen atoms. The rich get richer. Elimination reaction, forming a pi bond by removing atoms from adjacent carbons, the exact reverse of addition. Zaitsev's rule, the major product is the most highly substituted, most stable alkene. Remove H from the carbon with the fewer hydrogens. Substitutions, an atom or group is replaced by a different atom or group. Alkenes are benzene rings, reacting with halogens under UV lights or catalysts. Condensation, esterification, and imidation. 2 large molecules combine while splitting off a small stable molecule like water. Carboxylic acid plus alcohol turns into ester plus water, catalyzed by concentrated H2SO4. Carboxylic acid plus amide turns into amide plus water. Oxidation and reduction. In organic systems, oxidation means adding oxygen bonds or losing hydrogen bonds. Reduction means gaining hydrogen bonds or losing oxygen bonds. Primary alcohol oxidation path. Primary alcohol turns into aldehyde, turns into carboxylic acid using oxidizers like KMnO4 or K2Cr2O7. Secondary alcohol oxidation path. Secondary alcohol turns into ketone. Tertiary alcohols resist oxidation because their central carbon lacks an available hydrogen bond. Thermochemistry and energy changes. So calorimetry master, to quantify thermal processes, track energy conversion across systems and surrounding using Q equals M times C times change in T, where Q is the heat, M is the mass, C is the specific heat, and T is the change in temp. Mass is the surround, where M is, I already said this, and C is the specific heat capacity, 4.18 for water. And then usually water, the mass is 1 gram per milliliter. System surroundings energy continuity rule. Energy lost by the reaction equals the energy gained by the colorimeter water. So Q of the system equals negative Q of the surroundings. To determine the molar enthalpy change, the change in H equals the Q of system over N, where N is the moles of the limiting reactant, usually expressed in kg per moles. Phase change mechanics. During phase transitions, temperature remains constant because thermal energy goes towards breaking intermolecular bonds rather than increasing kinetic energy. Use the molar enthalpy of transition. So Q equals N times the change in H sub slash VAP slash fuse. Hess's law puzzle strategy. Goal: manipulate a set of given component equations to perfectly sum up to a targeted net equation. So isolate key reactants. Locate a primary reactant in your target equation. Find the component equation containing it. If it is on the wrong side, reverse that equation and flip the sign of its change in H, positive to negative. Scale, or vice versa. Scale coefficients. If the component's equation's coefficient doesn't match the target equation, multiply or divide the entire equation, including its change in H, by that scaling factor. Verify intermediates. So repeat for all key products, ensuring unneeded reactions. Intermediates cancel out cleanly on opposite sides of the equations. Sum the adjusted change in H values. Potential energy diagrams. These diagrams illustrate enthalpy changes over the course of reaction. Exothermic reactions. Reactions sit at a higher energy level than the final products. Change in H is negative, and heat is released to the surroundings. Endothermic reactions. Reactants sit at a lower energy level than the final products. Change in H is positive, and heat is absorbed from the surroundings. Activation energy. The initial energy barrier required to reach the high energy activated complex at the peak of the curve. The forward activation energy relates directly to enthalpy, so via EA reverse equals EA forward minus the change in H. And then kinetics, reaction rates. 1. Differential rate law and method of initial rates. The rate law relates the starting rate of a reaction to the concentrations of its reactants. Raised to the power is called reaction order. So rate equals K A M B N, where M and N are to the power of. Where K is the unique temperature dependent rate constant, while M and N represent the individual reactant orders. These orders must be determined experimentally and do not simply match the coefficients of the balanced chemical equation, but we do use that anyway. So problem: determine the rate law, overall order, and rate constant K with proper units using this experimental data set. So it gives you initial A, initial B, and initial rate. So find the order for reactants. Compare trial 1 and 2. B is held constant at something at 0.10, while A doubles during that 0.10 to 0.2. So 0.2 over 0.10 is 2. The rate changes from 4.0 times 10 to negative 5 to 1.6 times 10 to the power negative 4, which is a 4-fold increase. So 1.6 times 10 to the power of negative 4 times 4.0 times 10 to the power of negative 5 equals 4. Set up the exponent equation. So 2 to the power of M equals 4. So M equals 2. Reactant A is second order. Find order for reactant B by comparing another set of trials, and then, set up the same exponent equation. Assemble rate law. So rate equals K A to the power of 2, B to the power of 1. Overall order, 2 plus 1, which equals 3, so it's third order. Calculate constant K with dimensional analysis. So substitute data from trial 1. So, for example, plug in A 0.10 and B is 0.10, and then put in their exponents to find the value of K. Reaction mechanisms and catalysts. So a multi-step reaction mechanism is a series of elementary steps that sum up the overall reaction. The slowest elementary step is the rate determining step, RDS, which dictates the overall rate law. Reaction intermediates, chemical species produced in an early step and entirely consumed in a later step, do not appear in the net equation. Catalysts, reagents introduced early to accelerate a reaction and recovered unchanged in the final step. Catalysts speed up reactions by providing an alternate pathway with a lower activation energy, but they have no effect on the net enthalpy chains, aka H. Chemical equilibrium and Le-Chatelier's principle. Dynamic equilibrium expression, KEQ. For any reversible reaction, dynamic equilibrium, AA plus BB turns into CC plus DD. The equilibrium constant is K equilibrium constant equals C to the power of C times D to the power of D over A to the power of A times B to the power of B. Never include pure solids or pure liquids in any equilibrium expression. Their effective concentrations remain constant. Only include aqueous species and gases. Le-Chatelier's principle, stress response matrix. So add reactant / remove product. Direction of shift shifts right towards product. Underlying chemical kinetics rationale increases collision frequency of reactants, temporarily making Q less than K. Applied stress, remove reactant / add product. Direction of shift shifts left towards reactants. Underlying chemical kinetics rationale increases reverse reaction rate, temporarily making Q greater than K. Increase total pressure, decrease volume. Direction of shift shifts to side with fewer gas moles. Underlying chemical kinetics, reduce total particle count to relieve gas concentration stress. Applied stress, decrease total pressure, increase volume. Direction of shift shifts to side with more gas moles. Underlying chemical kinetics favors gas production to counteract the drop in pressure. Applied stress, raise temperature, exothermic, so plus heat on right. The direction of shift shifts left, K value decreases. Underlying chemical kinetics, the system shifts to absorb the added thermal energy. Applied stress, raise temperature, endothermic, heat plus on left. Direction of shift shifts right, K value increases. Underlying chemical kinetics, the system shifts to consume the added thermal energy. Acid, bases, pH, and solubility equilibrium. So weak acid / weak base calculations, ice tables. Unlike strong acids that ionize completely, weak acids establish a dynamic equilibrium governed by the acid ionization constant, Ka. So for example, HA plus H2O turns into H3O plus A negative, which turns into Ka equals products over reactants, and you do not include liquids or solids. Application strategy. So if the ratio of the starting acid concentration to its ionization constant is greater than 100, so HA initial over Ka is greater than 100, the change in concentration, negative X, is negligible. You can approximate HA equilibrium equals HA initial minus X to equal HA initial, which lets you avoid the quadratic formula. Solubility product constant, KSP, and precipitation dynamics. So the solubility product constant governs saturated solutions of slightly soluble ionic compounds. Example, MMXNS turns into Mn to the power of N positive plus Nx to the power of M negative, which turn into KSP equals M N positive to the power of M, X M negative to the power of N. So the coefficients. To predict whether a solid precipitate will form when mixing solutions, calculate the reaction quotient, Q, using the initial ion concentrations and compare it directly to the known KSP. So if Q is less than KSP, the solution is unsaturated, no precipitation occurs, more solids can dissolve. If Q is equal to KSP, the solution is at dynamic equilibrium and perfectly saturated. Q is greater than KSP, the solution is supersaturated. Ions will combine to form a solid precipitate until Q drops back down to equal KSP. Redox reactions in electrochemistry. So the ion-electron half-reaction balancing protocol, acidic media. So split into components, assign oxidation numbers, and split the net equations into individual oxidation and reduction half reactions. Balance non-O and non-H atoms. Balance all elements except oxygen and hydrogen. Balance oxygen atoms, add water molecules H2O to the side lacking oxygen. Balance hydrogen atoms, add hydrogen ions H plus to the side lacking hydrogen. Balance total charge, add electrons E negative to the more positive side to balance the net electrical charge. Equalize and combine, multiply both half reactions by common factors so their electron counts match. Add the equations together, canceling out matching electrons, water molecules, and hydrogen ions. Galvanic / voltaic cell architecture. Galvanic cells convert chemical potential energy from spontaneous redox reactions into electrical energy. The anode, the electrode where oxidation occurs, loss of electrons. This metal electrode typically loses mass over time. Miamonic and oxide, the cathode, the electrode where reduction occurs, gain of electrons. This metal electrode typically gains mass over time. Electron flux path. Electrons flow spontaneously through an external circuit from the anode to the cathode, alphabetically, A to C. The salt bridge maintains electric neutrality with the cell. Anions migrate through the bridge toward the anode compartment, while cations migrate towards the cathode compartment. And that's all.